now is you have to put it closer.
Okay, okay, that works. Okay, thank you very much for the introduction. And of course, let me thank the organizers for the kind invitation. And in particular, Luis Felipe, who is a colleague of mine at this department here in Natal. Before starting, let me also acknowledge my local collaborators. So Gislene, who is a postdoc at the physics department, my undergraduate students, and my collaborator from the International Institute of Physics, Marco Giampaolo. And before starting, let me also advertise a couple of workshops that I'm organizing. The first one will be at the end of this year in December in São Carlos, in the state of São Paulo, here in Brazil. And the topics will be related to systems with long-range interactions, quantum technology, and quantum simulations. And the other co-organizers will be people from São Carlos and Aristeo Lima, who is from Ceará. The second workshop, actually it's a program, will be a 2 weeks program here at the International Institute of Physics next year. The event has been approved and it will appear soon at the IIP website. And the topics, as you can see, are very broad. And it is essentially about the advances in quantum simulation with the ultracold atoms. My other co-organizers are Leonardo Fallani from Florence, Christophe Salomon from École Normale in Paris, and Luis Santos from Hanover in Germany. Okay, I will discuss mainly about physics, so I apologize if I will not enter in too much detail about the numerical methods that I will use to understand the physical systems that I'm interested in. But the main motivation behind this talk is related to the application of ultracold quantum systems to essentially quantum technology and quantum simulation. So the main purposes are related to quantum computation for the realization of fast and hopefully scalable quantum gates. There was also the talk by Sebastiano the day before yesterday that was mentioning these possible applications. Quantum simulation, of course, for the design of new types of interactions and the understanding of exotic phases. And the possibility of mixing different degrees of freedoms, like, for example, spins or fermionic or bosonic degrees of freedom, or both. You can think of a mixture of bosons and fermions as well. There are applications to quantum metrology. The main idea is to boost the sensitivity of some certain quantum devices. And the main point here is the creation and detection of entanglement or entangled states to, for example, interferometers or atomic clocks, which are really the most interesting and most, let's say, studied examples in this context. And finally, one can also look at energy transport, for example, the transport of excitations for the understanding of some natural interesting energy processes, like, for example, photosynthesis. And let me mention that although I will focus on coherent many-body dynamics, there are, of course, many interesting effects that can be studied with dissipation, of course. And in particular, if you look at energy transport in physical systems, in real physical systems, dissipation is a main, is of course always present. Then I want to focus on a system with long-range interactions in the ultracold regime. And this can be simulated essentially with 3 different setups, at least for neutral atoms, which can be either magnetic atoms like chromium, dysprosium, or erbium, which have a natural large magnetic dipole moment, or polar molecules like potassium rubidium or sodium potassium. There are several experiments around the world, and one of them is being set up in Recife, which is a city quite close to Natal, here in Brazil. And finally, setups of Rydberg atoms, which will be essentially the topic of the first part of my talk. And here again, there are many experiments, mainly with rubidium, or strontium, or ytterbium, or again with Rydberg ions that I will not talk about. Okay, so this is essentially the outline of my talk. I will the focus will be on crystallization, essentially with in the first part we talk about crystallization in lattice models, so in quantum spin systems. And this is related to a couple of experiments I've been collaborating with with two different groups, the group of Emmanuel Bloch in Munich, and the other one of Antoine Brouez in Palaiseau in Paris. Then we'll go to crystallization in free space. We'll mention some results that have been obtained in collaboration mainly with Fabio Cinti from Stellenbosch in South Africa, who is an expert on path integral quantum Monte Carlo methods with bosons. And finally, if I will have time, I will also talk about generalization of the previous context of the previous examples with dipolar bosons, which is a more recent results that I've obtained with Fabio, Alberto Cappellaro, and Luca Salasnik from the University of Padova in Italy. Okay, so going back just for a second on the motivations, let me mention that all the systems that I was talking about are essentially complementary, because you can explore different parts of this sort of diagram, where in the two axes we have the number of particles or number of spins that we can use for that we can really play with in our physical systems, or the coupling range. So you see here that we have trapped ions, which behave like particles with the Coulomb interactions, that essentially have a very long range, but on the other hand, you can control a very limited number of particles. Then here in the middle, we have Rydberg atoms that can be tuned, whose interaction can be tuned to be either dipole-dipole or a van der Waals. So it can either decay as 1 over r to the 1 over r cube or 1 over r to the 6. And then polar molecules, where you can study and magnetic atoms. You can study a quite larger number of particles, but they are slightly difficult to condense. And finally, you can probably the most known examples are ultracold atoms in lattices, where particles are not excited to some Rydberg state, for example, and they interact via typically either contact interactions or at most nearest neighbor interactions. And of course, there are many, many experiments around the world. Of course, you can interrupt me at any moment if you have questions, or you can feel free also to get in touch with me during the coffee break. Okay, let's focus first on Rydberg atoms. Rydberg atoms are essentially very similar to hydrogen atoms, where the electron in the external shell can be excited to a state with a very high principal quantum number. They behave as hydrogen atoms in the sense that the scaling of the energy with the principal quantum number is 1 over n squared. There is a small term here which is called the quantum defect that is order unity, so essentially the scale is not very much affected. Then one can look at the typical dimensions of these systems. They scale as n squared. And you can see here a comparison between a rubidium atom in its ground state, whose dimension is of the order of 0.5 nanometers, with respect to a rubidium atom in the state with n equal 43, and you see that the dimension is 250 nanometers. So they are really big objects. Then the lifetimes of these systems, of these atoms, are scales like with the n cube. So for example, for this rubidium atom, you have 45 microseconds, which is a very long time, for example, compared to typical electronic excitations in solids. But then probably the most interesting feature is the scaling of the interaction strength, because it goes like n to the 11th power. So it's really huge and very strong interaction compared to other physical systems that I was mentioning in the previous slide. Now let's look at the kind of prototypical Hamiltonian that we can look at. So suppose that we model these Rydberg atoms by a bunch of two-level systems. So these atoms can be either, the electron can be either in the ground state or in the excited state. And these two states are coupled by a laser field, whose strength is proportional to this parameter, which is called Rabi frequency. And this coupling here is represented, the Hamiltonian, by this sigma x coupling between the two states. Then, if the excitation is off-resonant with respect to the energy of the excited state, we have an additional term which is proportional to this parameter delta, which is called the tuning, and it counts essentially the number of particles in these excited states. On top of that, we have the interaction, this Vij term here, that essentially describes the interaction between particles in these excited states. So if they are in the ground state, or one particle is in the ground, the other in the excited, they do not feel any interaction. Whereas if both atoms are in these excited states, then they feel an interaction, this Vij that scales like n to the 11th power, and with distance it goes like a van der Waals interaction or a dipolar interaction, depending on the nature of these excited states. Now, you easily see that this is, of course, interesting also for the kind of topics that were discussed during this workshop, that if you substitute these n operators with the usual polymatrices, so this n is a projection operator to the excited state, you see that this model can be easily rewritten as in terms of a long-range Ising model with a transverse field proportional to the Rydberg frequency and a longitudinal field, which is the so-called detuning, proportional to the detuning. And related to that, let me also mention that this term here essentially acts as a sort of chemical potential for particles populating these excited states. So the larger is delta, the larger is the number of particles in these excited states. Now, it is also interesting to notice that, okay, it is an Ising model, but with some specific features that are related to the real physical system that we are simulating. So, for example, typical duration of experiments or a typical duration of the dynamics, of the coherent dynamics, in order for these excited states not to decay to the ground state, is of the order of few tens of microseconds. And within these time scales, since we are working in the ultra-cold regime, particles essentially do not move. They are frozen in their original configuration. And therefore, only the spin degrees of freedom are really relevant. There are no motion, there is no motion or hopping of the particles from one lattice side to the nearest neighbors, for example. The second important observation, which is also really crucial for applications, is related to the energy scales. Since, as I already mentioned, this Vij is really strong, is very large, and is typically much larger than the other two fields in the longitudinal and the transverse field. And this means this has a consequence, the so-called excitation or dipole blockade, that is quite similar also to the Coulomb blockade mechanism that appear in typical solids or electronic systems. And this can be easily illustrated just for a system of two particles. So the Hilbert space here is just four-dimensional. You can have either two spins pointing down, so two particles in the ground state, one of the two in the excited state, or both in the excited states. Now, since the interaction is very strong, but it decays with distance, if two particles are very far apart, they behave essentially as independent particles, which means that with your laser you can essentially switch the two spins from the ground state to the excited state simultaneously. But as soon as the distance becomes smaller and smaller, the probability of exciting this doubly excited state essentially goes to zero and vanishes. You see, below a certain typical distance, which is called the blockade distance. And this implies that we can study the dynamics of these systems in terms of a reduced Hilbert space, which is made of just two states, this GG state, both spins pointing down, and the so-called W state, which is a symmetric superposition of single excited states. So this W state for two particles is just an instance of a Bell state. And this was also discussed first by Yakst, Zoller, and other people, and Lukin and Fleischhauer back in the years 2000, 2001. And the interesting point is that you can write down an effective Hamiltonian, which is made just by a coupling between these two states, where the effective coupling here, the coupling strength, is increased by a factor √2 with respect to the original microscopic coupling. And of course, this is important, in particular, if you want to look at experiments, but also to applications, for example, in quantum computation, quantum information to realize quantum gates. Why is it so? Because you expect that the collective Rabi coupling scales for n particles as √n, and therefore the velocity or the speed of these oscillations increases by a factor of square root of n. This means that you can make, in principle, your system scalable, but also much faster, and therefore less affected by possible decoherence effects. Now, for n particles, the generalization is quite trivial. If all particles belong to the same sort of blockade sphere, which means that they all their reciprocal distance is smaller than this blockade radius RB, but they all belong to the same sphere, then you can expect that your reduced Hilbert space, reduced Hilbert space is still made of just two states. So the ground state or the state with zero excitations that I could just denote here with zero, and the generalized W state, which again is a state that is composed of a symmetric superposition of singly excited states. And therefore, as I already mentioned, the scaling with the number of particles of the omega, the effective omega is square root of n. And we have a bunch of experiments that are going on since have been going on since 2009 until very recently. I've been involved in a couple of them, as I was talking really at the beginning. The first one was realized in Munich, which consists of a system of particles loaded into an optical lattice and excited to a Rydberg state of rubidium. The other one is the Palaiseau experiment, where they use microtraps or optical tweezers, where particles are still rubidium atoms excited to these states. And here the flexibility is much larger in terms of the geometry of the array of atoms, of the lattice of atoms that you can play with. You can, for instance, look at single atoms or lines of atoms or square lattices or even triangular lattices with some sites which are not occupied. The kind of physical setups are in some sense similar, but the number of particles that you can play with is much different. So, for example, in this Munich experiment, you can really explore the scalability of the system from just a single particle to few hundreds of particles, whereas in this other experiment in Paris, since the distances between the atoms are much larger, you can go from essentially one particle to a few tens of particles. But in both cases, you see that if you look at the frequency of these Rabi oscillations from the ground to the excited states, then both experiments essentially reproduce this square root of n scaling of the effective Rabi frequency. Now, how can we go beyond this sort of superatom picture or of multi-particle qubit states? Well, there are several ways. In principle, one can just increase the system size, so breaking the so-called blockade by letting particles to be farther than to have a distance which is larger than the typical blockade distance. Or you can vary the so-called principal quantum number, which means that you either increase or reduce the strength of the interactions. And increasing or reducing the strength of interaction means that this blockade radius also varies. Or you can go fluorescently, just increasing the parameter delta. Or another scheme that I will briefly discuss in a moment will be the so-called Rydberg dressing. Now, this is again the experiment in Paris, and here you see that the blockade sphere, which is here represented by these shaded areas, can be varied by changing either the system size or the geometry of the system, like going from circles to some horse-track shapes or square lattices. And here the dots are the experimental results, and the lines correspond to my numerical simulations in systems. And here you see that the fraction, here we plot the fraction of Rydberg excitations, which means the fraction of Rydbergs with respect to the total number of atoms in the setup. Essentially varies from 1 over n, where the system is fully blockaded. 1 over n means that you have just one excitation on with respect to n particles, to a system which is not blockaded at all, so you can essentially excite all the particles at certain times. So these are just the profiles of collective Rabi oscillations that I was talking about previously. But again, the difficulty of simulating these systems, in the sense that there are many ingredients that you really need to take to consider, you see that simulations also, in some cases, for example, for these very large system sizes, cannot really address all the features of the experiment and are not able to reproduce the many-body quantum dynamics of these physical systems. Now, let me go back, let me take a step back and discuss the phase diagrams of these generalized Ising models. Well, in terms of these two different parameters, the transverse field and the longitudinal field, what you will expect is that, of course, if the transverse field is very, very strong, all particles essentially align along the direction of the field, and you will have a paramagnet here in this region here. On the other hand, if you increase the tuning delta and reduce the omega parameter, what you will expect is that the system becomes more and more classical. Why is it so? Because if you, for a second, just neglect this term here, and you look at the Hamiltonian composed of this delta parameter times these projection operators into the excited state and the interaction terms here, you will see that by increasing the delta parameter, you can squeeze more and more excitations in your linear chain, for example. This is just a one-dimensional chain for simplicity. And then you will see a sort of staircase of excitations by increasing the delta parameter. So, for example, here, for low detunings, you will see that you have one excitation every 1, 2, 3, 4 lattice sites. Okay? Here you have 1/3, 1/2, etc., until the system becomes fully loaded with the excitations. Okay? But again, this is just a classical Hamiltonian, so it's just a sort of classical Ising model. The interesting thing is related to the possibility of realizing experimentally these kind of phases, either in 1, in 2, or in principle also in 3 dimensions. Now, this problem is very similar to what Sebastiano was talking about in the sense of adiabatic preparation of certain quantum phases. And the reason is that here the system experimentally are typically initialized where in the state where all the particles, where all the spins point down. Okay? And now we want to devise a protocol where essentially by tuning or by changing our two external fields, the omega and the delta parameter, and devise a path in this parameter space in order to address this to reach at the end of our dynamics these many-body crystalline phases. This is instead a two-dimensional example that I will also show some simulations in a moment. But let's look at the idea, the idea of the dynamics that we have to look at in order to obtain these phases. Suppose again that we look at the phase diagram or at the energetics of just a classical model. So we disregard for a moment, we neglect the first term here in the Hamiltonian, and we just change the detuning. As I was saying before, what we expect is that first for negative detunings we have we don't have competition between this term and this term, because of course the ground state will made of 0 excitations. So you see that here this term here essentially counts the number of particles in the excited states, and this also, if we are considering an antiferromagnetic model where this Vij is positive, of course does not become competitive to put interactions in the excitations in the system, because this will increase the total energy. Now, on the other hand, if you start to increase the detuning, there are manifolds of states with a different number of excitations that will start to become competitive. And the reason is that, again, for positive delta, this term here becomes negative, and this term here is positive, but may not be able to compensate the effect of this longitudinal field. Then, increasing more and more the detuning, we see that manifolds of states with 2, 3, and in principle 4 and 5 or more excitations will become favorable. Now, the point is that we are dealing with a quantum mechanical system, so it's not enough to just increase the detuning and say, okay, and see what happens. Because these can only happen dynamically. So the idea is that we want to switch on simultaneously the tuning here and the transverse field in order to be able to end up at the end of our dynamics into a state for a well-defined value of the detuning with a well-defined number of excitations. These states are typically called Fock states, so, which means states with a well-defined number of excitations. So of course you see that from the quantum mechanical point perspective, what you will see here is a sequence of so-called Landau-Zinner crossings as soon as you switch on your transverse field. And of course, the faster your protocol will be, the lower will be at the end of the dynamics the fidelity of the expected state with your dynamically evolved quantum state. Okay? And this is still connected, of course, with the adiabatic theorem in quantum mechanics, or the so-called Landau-Zinner problem, which is also a very classic old problem in quantum mechanics. Now again, I mean, here I'm just showing the final result. If you properly tune the dynamics of these, the dynamics of these two external fields, you see that the expected result, or the ideal result, which means that fidelity equal to 1, correspond to the steps, so to the staircase of excitations by increasing either the length of the chain or the detuning. And here the dots are the experiments, so you see that there are these plateaus, or the experiment is able to reproduce quite nicely these plateaus, as well as our numerical simulations, which are done essentially with the same parameters of the experiment in Munich. Now, since I want to talk a little bit about the methods, or essentially how this idea works, let's assume that we are working in this two-dimensional parameter space where I put the Rabi frequency on the x-axis and the tuning on the y-axis. So our system is initialized with 0 Rabi frequency, so this omega is 0. The system is fully classical, but with 0 excitations as well, because the tuning is assumed to be negative. And then we want to slightly or very smoothly go along this path, which is a sort of optimal path in this two-dimensional parameter space, in order to end up at this time equal to 7, if you wish, into a state with the maximum fidelity to obtain 3 excitations. Okay? So this detuning, which is roughly 700 kilohertz, is expected to present for this detuning, we expect 3 excitations. Okay, so what is the dynamics? You see that here we plot in the lower part, we plot the dynamics of these, the time evolution of these two parameters. So this is the detuning, and this is the Rabi frequency. Okay, so if you plot both, if you do a parametric plot in this two-dimensional parameter space, we are going essentially along this black line here, black path. Okay, what do we expect from our simulations? Well, you expect that at the beginning, the probability or the fidelity with the states with 0 excitations is very high. Essentially, it's 1 at t equal to 0, but then it decreases. Then there are other states, other Fock states with 1 excitation that start to become relevant, for example, at times 2 or 3, where from the statical point of view, so let's say from the thermodynamical point of view, we expect a paramagnet. Then at other intermediate times, like 4 and 5, there are states with 2 excitations that start to become relevant. And then you see that all these probabilities, P0, P1, and P2, essentially vanishes, or should go to 0 quite quickly. And whereas the probability or the fidelity of our many-body state with the Fock state with 3 excitations is relatively large, so it's of the order of 90%. And let me say that here we exploited this adiabatic path, so we made our path as adiabatic as possible within our experimental constraint, within the experimental constraints, which are essentially due to the fact that the dynamics cannot last for too long, otherwise the Rydberg states start to decay. So you see that this path is very, very fast. So in 4 microseconds, we are able to obtain a many-body quantum state which has a fidelity of roughly 90% with the state with just three excitations. So this is really quite remarkable results. But let me also say that if you want to go beyond this adiabatic scheme, there are techniques, like for example the so-called crab, which is quite well known in this area, that allows essentially to reach within the same time scales a fidelity which is very close to 100%. Okay, so these are also the comparison between theoretical and experimental results. And here in the right plots, we show the distribution, the space distribution of these excitations that emerge along the time dynamics. And you see that if you consider just a sort of quasi one-dimensional system, which is made of chains of 3 parallel chains of 23 atoms, then we observe that at intermediate times it start to appear these 3 excitations, 2 at the edges as one at the center, which is also expected by simple energetic calculations, if you wish. Why? Because since the system is long range, it is more competitive as a configuration where the two excitations are relatively far and one is in the middle. And at the end, you see going along this path at time equal to 7, we end up really with two well-definite excitations at the edges as one in the middle. And of course, at intermediate times, there are states with 0 excitations, states with 2, states with 3, that are both that are all competitive in some sense. We don't see a great visibility of these 3 excitations that we expect from calculations based on the classical model. Okay, so what is the numerical methods that I'm using? Well, you may wonder, you may ask yourself, okay, but look, this guy is simulating systems with, is looking at systems with a few tens or even hundreds of spins. This, in principle, should be crazy, because why is it so? Well, because the Hilbert space increases exponentially with the number of spins. So we have two states per particle, and then with 2 particles we have 2 by 2. You have 4 states. With 3 particles we have 8, and so on and so forth. So the scaling is really exponential with the system size. But on the other hand, we are looking at a specific physical system where the total number of excitation is essentially limited by the longitudinal field here. So if you don't take delta, which is too large, which means that this term is not really too much competitive with the long-range interactions, so still the long-range interactions for a system, many particles are dominant, then you will expect to be able to, that your manifold of states will be limited to a certain number of Rydberg excitations. Okay? This essentially tells you that you can completely neglect a full bunch of states with many excitations. This allows you to work in a reduced Hilbert space where the total number of states is not exponential, does not increase exponentially with the system size, but just polynomially. The physical idea behind is a sort of renormalization group idea, if you wish, but it's even simpler than that. So the point is that I discussed at the beginning the so-called blockade mechanism, and here we are essentially applying the same the same mechanism by cutting or reducing our Hilbert space by not considering all the states that have 2 close-by excitations. 2 close-by means that 2 excitations that are within the same blockade sphere. And therefore, we are left, for example, with states that have excitations at distance 2, distance 3, distance 4, and so on and so forth. Whereas all the states that contain 2 excitations which are very close by are so far in energy that essentially they will not be able to be excited dynamically. Okay? So by working in this reduced Hilbert space, which means a few tens or few even hundreds of thousands of states, we are able to do essentially the exact dynamics, or if you wish, looking at the lowest energy states of these manifolds. Okay, so if there are questions, if there are no questions, I will go on. So I have still some time. Let me just discuss very briefly the other possibility to go beyond the so-called blockade scheme that I was discussing at the beginning. So the idea is to use a mechanism which in atomic physics is called dressing. That I will not go into the details of this mechanism, but let me mention that the main point, the main outcome of this coupling scheme is the possibility of tuning or changing the shapes of our interaction potentials between the particles, and also increasing the coherence times up to few hundreds of milliseconds or even to some seconds. Now, even if we are in the ultra-cold regime, if we look at timescales of the order of few tens or hundreds of milliseconds, within these timescales, particles are allowed to move. And therefore, in our effective Hamiltonians, we will need to consider an effective motion, so a kinetic term here. Okay, here there is a sum over all the particles, plus an interaction, which has the shape of a so-called soft core potential. Soft core means that still it decays as a power law for large distances, but then for small distances it saturates to a constant. So instead of the typical van der Waals or dipole-dipole interaction that diverges, so it has a sort of hardcore nature in it, this soft core potential it saturates to a constant. Okay. So there are many, of course, several possibilities to simulate efficiently these systems, at least for bosons. One way is to look at the so-called Gross-Pitayevsky equation, which is a mean field approach based on the solution of this nonlinear Schrödinger equation. So the nonlinearity comes from this interaction term here. You see that this term is proportional to psi square, which is the wave function of the condensed system of bosons, times psi of R. And these two wave functions are of course evaluated at different points, since the interaction here is non-local. And it's interesting to see that although we expect a dependence of two different parameters, essentially a scaled density, rescaled density, where the density here, the physical density is rescaled by the blockade parameter that I was defining at the beginning, and this alpha parameter, which is a rescaled interaction strength. Okay. Now, it is interesting to notice that within this mean field scheme, actually these two parameters combine and into a single parameter, which is this alpha, which is just the product of these rescaled interactions times the rescaled density. So what is the outcome? I will not go into the details. These results have been published some time ago, and they are also supported by some more elaborated pantheteral quantum Monte Carlo calculations that were done by my colleague Fabio Cinti. So the outcome is that for small interactions or small values of this rescaled or this parameter alpha prime, we expect a superfluid phase where essentially particles are very mobile. They are completely delocalized. And if you compute the superfluid fraction is essentially equal to 1, at least at the temperature. Then at intermediate interactions, what one gets is a so-called cluster supersolid phase, where the cluster supersolid comes from the fact that you still preserves some remnant superfluidity, but on top of that, the system breaks translational symmetry, which means that which is due to the fact that you see that particles clusterize into some droplets, okay, with a few atoms in it, okay, but still the particles are preserve some mobility, so they can jump from one droplet to the other, and this is the reason why there is still some superfluidity in the system. And finally, of course, if you increase the strength of the interaction much beyond the transition from the supersolid to a sort of classical state, you end up into a normal crystalline phase where particles are bounded essentially to stay within the same droplet, so they are mobile. You can think of a sort of Bose-Einstein condensate of clusters here. And so they cannot hop from these clusters to the nearest neighbors. So they are limited in some sense to this. They are constrained to move within these clusters. Okay. Now, another interesting point is that, of course, these clusters, at least in 2 dimensions, form a regular triangular lattice. If you work in 3 dimensions, you could expect more a competition between different lattice structures, whereas in 2 dimensions they can just be triangular. Okay. Okay. On top of this, one can also look at excitation spectra of these phases. So it's interesting to mention that there is a nice analogy with other physical systems, like for example liquid helium or superfluid helium, or a system of dipolar atoms that if I will have time, I will discuss very briefly at the end. And the main point here, if you look at the excitations, so to study excitations, one typical way is to essentially expand our quantum field around the classical solution given by the Gross-Pitayevsky. So the quantum fluctuations are given by this delta psi parameter. And the idea, if you plug this expansion back into the Gross-Pitayevsky, you end up into a system of coupled non-linear equations, which are called, consist of the so-called Bogolyubov-Dejean set of equations. And by of course linearizing and solving these equations, you end up with some set of eigenvalues, which correspond to the excitation spectra of your many-body phase, as a function of k, of this k parameter. Okay, the momentum of the excitation, and it is interesting to see that for the superfluid phase, since the interaction is non-local, you end up with the so-called Roton-Maxon profile, where the Roton corresponds to this local minimum in the excitation spectrum, and the Maxon corresponds to this maximum in the omega over k excitation. Okay, whereas for small momenta, the excitation, of course, is linear, and this is also due to the superfluid nature of the system. A similar spectrum, as I mentioned, is also very well known in superfluid helium, or in other systems that display long-range interactions. Probably another interesting excitation profiles can be obtained in the modulated phases, either in the supersolid or in the crystalline phase. So this corresponds to the supersolid, and this corresponds to the crystalline phase. Of course, the mean field, or this set of Bogolyubov-Dejean equations, are not able to reproduce efficiently the crystalline phase, because still we impose by hand that there is some coherence in the system, and this leads to some remnant superfluid band here, even in the crystalline phase. So the continuous lines are the solutions of these Bogolyubov-Dejean equations, whereas the dots correspond to some numerical calculation based on quantum Monte Carlo that were done by Sebastiano Saccani and Massimo Boninsegni. And finally, let me just flash on this generalization of these quantum phases with dipolar atoms. The motivation, again, is connected to some more recent experiments that have been done mostly in Stuttgart in the group of Tillmann-Pfau, and in Innsbruck in the group of Francesca Ferlaino. So they used 2 different atoms to realize these experiments. The first one are done with dysprosium, the other with erbium. They both display a very strong dipole magnetic moment. And of course, the interest here, and the difference with respect to the Rydberg-Drest case, is that the interaction is not only long range or finite range, but is also anisotropic. So depending on the orientation or the relative orientation of these dipoles, interaction can be either repulsive or can be attractive. So 2 dipoles that sit one on top of the other, so in this head-to-tail configuration, display an attractive interaction, whereas 2 dipoles which are close by but they are parallel, so along the same line, they display a repulsive interaction. Again, one can write down an effective mean field equation, which is essentially a generalized Gross-Pideski equation, where here the nonlinearity comes from this dipole-dipole interaction. And physically, the system is described by this epsilon parameter, which is the ratio between the dipole-dipole interaction length and the so-called scattering length, which is an effective description of the contact interactions between two quantum particles at very low energies. And it turns out that for epsilon smaller than 1, we expect the superfluid phase, so in complete similarity or analogy with the system of Rydberg dressed atoms. Whereas for epsilon larger than 1, we get an instability and therefore a collapse. What does it mean physically, epsilon larger than 1? Essentially it means that the contact interaction that is always present between this particle is not able to compensate the effect of dipolar interactions. So of course for two dipoles it is more convenient to sit one on top of the other, and this means that essentially all particles want to do that at the same time, and so the system is expected to collapse at the same point. So of course in that case we don't expect any interesting feature. On the other hand, experimentally, it was seen as basically the opposite of what I was saying. So for epsilon larger than 1, which can be obtained, for example, by tuning the scattering length by the so-called Feshbach resonances, what you will see is a modification of the profile from a sort of pancake structure here into a set of droplets, which are quite similar to the droplets that I was discussing in the Rydberg case. Droplets which are elongated along the direction of the dipoles, and therefore they can be called either droplets or filaments here. So this brings to our attention a set of interesting theoretical questions that I will not be able to discuss in detail, but let me just mention them. So the first one is that whether these filaments or droplets are stable as a ground state of the system, even for of course for epsilon larger than 1. What is the description beyond this generalized mean field equation? So because of course this mean field equation does not support this solution. The other questions are whether these filaments are superfluid and whether there is a supersolid phase for dipolar bosons. And these questions were addressed in our recent paper. So the point is that by looking at extensive quantum Monte Carlo simulations, we end up with a phase diagram that is made of 3 different phases. A superfluid phase, so where essentially the system is uniform, totally uniform, particles are delocalized. A filament phase, where there are these filaments parallel to each other that arrange in a quasi-regular way, so it's not exactly triangular lattice or a square lattice as it can be seen from this picture. And finally, an unstable or a cluster phase, which is not really unstable, so where it's made of just this cluster which arrange randomly in the three-dimensional space, and dipoles are still aligned vertically, so they are slightly elongated along the vertical direction. Okay, so regarding an effective description, so I have just 1 minute, so I will jump quickly to the conclusions. So the main point here is that we need to generalize this mean field equation by adding an additional term here, which is proportional to psi cube, so it's a sort of contact interaction that comes from the regularization of the so-called Li-Wang-Yang contribution that was discussed first by Li-Wang-Yang back at the end of the 50s, and then extended by Lima and Pelster around 10 years ago in the context of dipolar interactions. Now, if you do that, if you include this term here, which is competitive to the dipolar term, you end up into a relatively slightly different mean field phase diagram, or beyond mean field phase diagram, that supports these filaments. Okay, so this is really an interesting feature where mean field breaks down, but with the addition of a properly regularized term, you can actually show that these phases are really physical, and in principle are stable as a ground state. So I will skip these details. Let me just jump to the conclusions or quickly flash on them. I was mainly focusing on crystallization phenomena, either in lattices or in free space. The first part, I discussed some results, both numerical and experimental results of Rydberg atoms in lattices. Then I quickly mentioned some interesting crystalline phases in free space with systems of that interact via soft-core interactions. And finally, I flashed on the generalization of the second part in the case of dipolar interactions. And finally, let me mention my collaborators for these works. So for the last part, Fabio Cinti and Luca Salasnik and Alberto Cappellaro from Padova in Italy. And then the two experimental groups of Emmanuel Bloch in Munich and Antoine Brouez in Paris. And finally, let me thank all of you for the attention. Thank you very much.